So go away.
Thank you. Yeah, so we kind of deliberately chose this somewhat provocative title. In fact, Simon was already complaining to me multiple times yesterday that this title was too cryptic. I'll try to reveal to you what we mean, and I'll start actually with the quote. Before that, let me just quickly introduce my co-authors on this paper, Chen and Kutang at the Tsinghua University, and Yan Chu Liu is at the Lausanne College. All right, so I'm going to start with a quote, and I apologize at first. I think this quote might stir some complex feelings among people in the audience, especially when people who work on structural models. So certainly did to me when I first read it. So I'm just going to read like some highlights of it. So it starts with this famous quote from George Fox: "All models are wrong, that's not useful." But let's cut to the chase of the bottom part, right? So this is by the way, the chief editor of The Wired magazine was commenting on this big data revolution, and he was saying that today companies like Google, which have grown up in the era of massively abundant data, don't have to settle for long models anymore. Indeed, they don't seem to need data models at all. Right? That's what I meant by complex feelings among theorists in the audience. You know, are we being kind of be replaced by all these kind of completely data-driven exercises? I'll give you an answer at the end, but let me go forward. I changed the topic a little bit and changed to another kind of thought experiment. Right? This is basically what would you do if you're trying to train a robot to play pool? Right? So you can imagine doing this in a completely data-driven way, and the way to do that is basically provide some labeled data. You try to record. These are the kind of inputs and outputs. So input could be the shot angle, the speed, the position, and so on. And then the output obviously will be recording what the outcome will be, right? So what direction the ball is moving, at what speed, and so on. And we know that this could potentially be done, especially with all these experts in the audience on the complex machine learning models. This is not that complicated a job to do. But we also know that we need potentially a lot of data because the problem can quickly become complex in a real life setting, and generating this large amount of labeled data could be expensive. Right? So that's one caveat. And if you remember what you learned in high school physics, we actually have a very simple but beautiful theory of elastic collisions, which actually tells us a lot about how to predict ball movements without observing any data at all. In fact, we can use very simple two equations. One is the conservation law of linear momentum. The other one is conservation of kinetic energy. Right? That would actually allow you to solve completely what's the outcome of the two balls hitting each other under the set of assumptions the model requires. But quickly can point out the weakness of the model as well, because this model could be, and probably is, misspecified, and there's going to be all kinds of caveat can bring to the prediction of the model, which means the prediction can be far from perfect, right? But with this two in mind, I think the intuition is pretty clear. So if you already kind of know a theory that drives the predictions to a first order, that should be reasonable. Why are we abandoning it? Why are we just completely doing this in a data-driven approach? In fact, is there something in the middle, right? Can we kind of take the best of both worlds and try to build a more predictive, powerful predictive framework that can benefit from both the theory and the empirical work? And the answer that we provide is through something called the transfer learning framework. We show that there's actually a very easy way to bring the economic insights in our models to this learning problem. In a way that can be easily, almost seamlessly, kind of matched together with what we could potentially learn from the data. Okay? And to put it in very simple words, basically, first learn from theory and then learn from data. And you see that the performance, at least in the empirical setting, experimental setting, is pretty good. Okay, so that brings us to hope that potentially the models we try so hard to work on, we spend countless nights coding about it, could actually benefit us in terms of real life predictive work as well. Not just in terms of counterfactuals. Obviously, that's kind of a go-to place when we defend structural models with BLS. Okay? All right, so I'm going to try to first introduce the first part of the sentence, essentially, how to learn from theory, and then we'll talk about how to combine that with the data. And how to learn from theory actually is very much built on the earlier work I did with Simon and Anton. So I'm going to do a quick review of how you can possibly learn from theory. So to put it in simple terms, learning from theory is basically try to learn the structural restrictions we impose on the data. right? So whatever models write down, let's say some kind of equilibrium model we write down there, like Marlon was presenting earlier today, essentially imposes some kind of a cross-equation restrictions among data that are exogenous and potentially endogenous quantity as well. And these restrictions are essentially the essence of our model, right? So rather than kind of letting it play out through our kind of a structural model assumptions and the Bellman equations or HJB equations, we could actually treat it more or less as a black box, right? So the inputs are the parameter states, and output are these equilibrium quantities. And the mapping between the inputs and output can essentially be treated as if it's a black box. And we just try to represent this black box mapping as accurately as possible using, for example, a neural network. This is indeed the work that we did in the earlier collaboration with Simon and Tom. The idea essentially is, let's think about a set of economic restrictions summarizing a model given by this equation here, f of s being the state and theta are the structural parameters. Y is the output variable. Okay, so for example, it could be the equilibrium price, and these could be some state variables that drive the price, and the other parameters here, such as preferences and the endowment process parameters as well. By imposing some hierarchical prior on the structural parameters, then you'll be able to derive, right, together with the economic restrictions, some joint distribution between the x and y's. And remember again that x includes not only the state variables but also the parameters. Okay, so this is kind of the starting point. Now you can draw as yes, please.
You don't want to answer this right now, it's fine, but our models are often saying
oh, absolutely, yes.
Sort of like where's the epsilon?
Yes, I deliberately drop it out in this case here, right? So in a way, there's going to be subject to this kind of the stochastic singularity problems that you're talking about. Absolutely. Well, I was trying to keep it simple here, but you're absolutely right that the restrictions in the end just need to imply some joint distribution that is different from the kind of distribution without restriction. So there is a movement from the kind of prior about how data is distributed to the posterior, and which is affected by the economic restriction. It doesn't have to be no error terms at all. But to keep the discussion simple, I want you to still think about a setting where we can derive some predictions about the y variable that is without error. We can easily modify this frame. Okay, so now let's imagine we can draw data from these joint distribution of x and y. Right? So we're going to be jointly pulling, drawing data that is including the state variables, the parameters from the x as well as the output y variable. Right? That basically involves solving these structural model many times under different parameter combinations. So potentially quite painful, but it can be done. That would be the training data that you would use to train a neural network. Right? So at this point, you can take out your favorite network structure. For example, just a simple feed-forward network would do the trick here. And you can basically try to look for a particular network over here within the class of networks you're working on to minimize some empirical loss. That's essentially how you would be able to train a neural network to inherit the economic restrictions that are embedded in our model. All right, so I already kind of explained what I mean by learning from theory, essentially, which is trying to get at these economic restrictions. But there's some advantages here that are worth discussing, and I'll go into more detail for those of you who are coming to tomorrow's lecture session. Some of the benefits we point out in our paper include, for example, for one, you know the true data generating process here, so there's no concern about the errors. Of course, there are going to be some numerical errors when you're trying to solve this model numerically, but by and large, it's kind of absent or free from the usual measurement errors that we have in the data. The second thing is that the neural networks are known to be very expressive in the sense of approximating power. So this famous universal approximation theorems, which apply not only to shallow networks, but also to deep networks in somewhat different ways. And there is actually a large literature in machine learning theory about this. Yes?
I'm trying to understand the distinction between, like, say, I've solved a model using a Bellman method or something, and I have a policy function surface.
Yeah.
So I have the correct solution to the model at a whole bunch of points.
Yes.
Are you basically just saying, let's represent those points with a neural net? Or are you saying something different?
We're representing a mapping, right, from these states and parameters to the outcome such as the policy function using a new.
But I have the policy. My point is I already have the policy.
Correct. So bear with me. You're right. You might be wondering, why do I need to present a separate because after all, we're in this paper, we're trying to teach the machine what the economic model is. We don't want to feed these kind of the structural functions that we derive from our model to the machine. This is something that we have a hard time understanding, whereas these neural network structure is something that can easily work with.
The point is that in the real world, it's going to see data generated from the, okay. So it's like indirect inference.
You will become more clear in a second why we want to do this translation. Now, the purpose of doing this mapping in my paper assignments for different purposes. It's because even though you might know that function, or maybe that functions implicitly exist out there, evaluating many times can be very costly. So maybe providing a mapping still be useful because it's kind of like a lookup table. Yeah. All right, so I think it was too fast there. Last point here, which is also worth mentioning for those who are curious about this approach, is that actually, if you have the right kind of a problem, in particular, a large class of economic problems fit into that category because we're essentially calculating some kind of expectations. And if you have suitable activation functions, then there are these very nice results showing that you can effectively overcome the curse of dimensionality, right? So in particular, we just mentioned that generating a large training sample can be very costly if you have to solve your model many times on the different parameter configurations. But the good news is that under the right setting, typically having to do with the regularity conditions about the smoothness of the function, you can actually show that the sample size required to achieve certain level of approximation accuracy grows not exponentially, but rather polynomially in the dimension of the problem, which is actually a big kind of a piece of good news in terms of how you might want to build these kind of surrogates. But putting this aside, I hope you can now get a kind of a basic idea of what I mean by learning from the theory, right? Which basically want to build a network representation of the economic restriction that are embedded in our model. All right, so this is a slide that's advertising about the speed of the computation, but in the interest of time, let me move forward. Talk a lot more about that in the math lecture tomorrow. But now we can get to the core kind of part of what's kind of really new what we do in this paper. This is basically now thinking about ways to combine the knowledge from the theory and the data. So we kind of already know that the network trained on the simulated data from these structural models inherit the restrictions. In particular, the information that is embedded in these restrictions are inherited by these parameters, right? These network parameters that we train from the simulated data. So now the hope is that maybe these parameters, in particular this restriction more generally that we inherit from the structural model, can now help us regulate the way we learn from actual data. And we know that when we train a neural network more generally in machine learning method on real data, we suffer from these bias variance trade-off considerations in particular, right? If you have a model with so many parameters and the sample size you have is limited, right? These bias variance trade-off can be in particular not beneficial for training large models and capturing potential nonlinearity embedded in them. So the hope is that maybe these economic restrictions that we are bringing into this problem can actually help us regulate this learning problem. So in particular, the idea is that we don't have to impose these restrictions like literally, right? We can basically let us help guide us in terms of looking for the parameters that will fit the data the best. Potential benefits include variance reduction. You also see that it's going to make the learning from the actual data much faster in terms of convergence rate. And finally, something that's worth mentioning is that you can actually get away with training large, complicated networks with a much smaller empirical data size. Right? These are the potential benefits you can get from doing this approach. Now, this idea is, by the way, nothing new, right? It's actually has been always in the literature. For example, you think about structural estimation, the bread and butter of structural estimation is indeed impose these significant restrictions in terms of improving the efficiency of our estimation, right? This is a long literature in, for example, rational expectation econometrics, exactly doing this. And then there's a slightly different approach, which is actually more related to what we're doing today, is this kind of a Bayesian VAR approach, in particular, a school of Bayesian VAR that uses informative priors developed from the models. So it goes back to earlier work by Don Liederman and Sims in 1984, which uses this random walk as a way to generate an informative prior for estimating VAR for macro variables. But also later on, these Minnesota-style DSG models have been kind of introduced into this literature. Essentially, the idea is quite simple. You would generate data from these DSG models, which I'm going to talk about in more detail in a second, right? This simulated data would then allow you to form an informative prior of the VAR parameters. You would then use that prior, take it to the actual data, do the Bayesian update, and get a posterior. And that posterior will now combine information from both the structural model as well as the real data. That's kind of the idea. And that's exactly kind of the idea we're trying to leverage on over here. So this is exactly what I was talking about, so I should have done there, right? So this procedure is simulating time series data from DSG model. They, in the paper by Frank Shortheit and Negro, they use a monetary DSG model, which is pretty standard. They have to have a kind of hyper parameters on these determining the hierarchical prior on the parameters. So would they be able to draw, right, the model implied quantities such as investment output and the inflation predicted by these models on the different parameter configurations. And they will fit the VAR on this simulated data effectively. And then they would update the posterior using the actual data. Okay? So our approach is in spirit very similar to what they do here. Obviously, we want to generalize this approach to work with nonlinear models, as you will see, right? So because we work with neural networks, we don't have to be confining ourselves in the space of linear process such as VARs. But also, it is not strictly a kind of a Bayesian approach. As you'll see later, we put some kind of experimental analysis on this and showing you that effectively the usual intuition of the prior posterior actually doesn't quite apply to our setting over here. Okay, so we'll make this more clear in a second. All right, so now let me explain to you a little bit more about what is transfer learning in case you're not quite familiar with this. We have already mentioned ChatGPT a few times in this conference, and the transfer learning is very much behind these large language models that was kind of driving the ChatGPT. So essentially, transfer learning basically uses these so-called pre-trained models on very large data sets, okay, to accelerate the learning on smaller data sets. So it automatically sort of separates these problem into two different sets. One is the pre-trained model on large data sets. This is what we call the source domain, using the jargon of transfer learning. And then learning on those smaller data sets or adapting the pre-trained model on the smaller data set is called the target domain. Okay. All right. So just to give you examples, for example, in these large language models, right? They are these gigantic pre-trained models using essentially all the data you can find on the internet, so to speak. And then you can take that pre-trained model for more specific tasks. For example, you are only interested in doing sentiment analysis for a set of data on Wall Street Journal articles. Then you can actually fine-tune that pre-trained large language model on this particular corpus of text, and you'll get much better results. But the training will be significantly accelerated because you're benefiting from a pre-trained large language model rather than starting from scratch. Right? So that's kind of the idea. So in our case, what is the mapping between the source domain and target domain? Well, by now you can already guess it. Our source domain is our economic model, right? We don't want to start from scratch and learn from data. We want the simulated data from the structural models we built to provide essentially a pre-trained model for us. And then we will take that, just one second, we'll take that model to the target domain. This is where you finally bring the actual data and fine-tune this model to fit the actual prediction exercise, hopefully performing better. Yeah.
Does it matter which one comes first? That is, whichever one comes first, do the weights on the model?
That's an excellent question. The answer is absolutely yes. I'll show you why that's the case. We think. Well, I have a caveat here. We have nothing that's kind of provable results. The rest of the paper is all going to be basically based on some kind of empirical exercise. So it's all conjecture and intuition rather than theorems. All right. So I was telling someone this morning that I think our paper here is going to be the paper that has the least number of equations in this whole conference. I think that is still true, but I'm going to show you just something to clarify the notation. So let's imagine that here's how we're going to do this in the source domain. Right? So in the source domain, we have a kind of pick a particular network structure. Again, the network structure is not important, but we're going to pick, for example, a feed-forward network with LA layers, and it's denoted by this phi function over here. It has the activation function sigmas, and then these are the weights. Right? So in particular, the weights are the ones we're trying to learn from training these on either the simulated data or the real data. Okay, so we're going to draw this training sample, which comes in pairs of xi's and the f of xi's from this joint distribution I was talking about earlier. Okay, so this is the model implied distribution. All right, and then in the source domain, we do a very standard training exercise, which is try to minimize some empirical loss by choosing these weights parameters in our neural network. In this particular setting, we are using withdrawing loss function built on a couple of different objectives. It has to do with the particular application we're working on, which I deliberately didn't mention until this point because it's a finance-based application. I fear that it will turn away the majority of the audience in this lecture right away. So that's why I was being a little bit hand-wavy about that. You'll see that in just a second. But rest assured that this methodology, I think, is general enough that can be easily applied to more kind of economically focused applications. Okay. All right. So this is what we would do over there. So in our example of option pricing, the reason we want to use a multiple objective is because we don't not only want to fit, for example, option prices over here. We also want to fit the Greeks, right? These deltas and vegas and so on. These kind of derivatives of the function with respect to certain state variables, which have a lot of interest empirically. Okay. So that's pretty straightforward. Now let's go to the target domain. All right, so in the target domain, we basically repeat essentially the same exercise. We inherit the network with exactly the same architecture. There's no need to change anything there. We also inherit the parameters that we learned from this simulated data in the first place. Right? But now we're bringing the actual data. So in the actual data, of course, there are no theta in them. So the actual data will be these inputs minus the parameters and the outputs we observe in actuality. We're going to try to minimize another loss function. In this case, we're simply minimizing the mean absolute pricing errors for these option prices in observing the data by choosing these parameters. But the important thing again is that we're not starting from scratch. Right? We're not initially randomizing these parameter values, but rather we're using these parameter values to learn from the first stage. Okay. Now here is a key point there, and is related to your question earlier, which is these reason that we do the kind of train the pre-trained model using simulated data first, and then kind of adapt it to the actual data, is because in the second stage when you're training this model over here, it is very important to do the fine tuning, which is basically a fancy word to say that you want to learn very slowly. You don't want to kind of drastically move away from these initial parameters, which essentially waste all the work we've done in the first stage. So you want to choose very small steps, learning steps. You also want to use a significantly smaller number of epochs so that you don't actually let the actual data influence you too much. Now, exactly what's the optimal kind of values to choose? Obviously, we don't have any theory to kind of rigorously argue about this, but in our empirical kind of exercise, you see that the performance can be substantially improved if you follow this kind of strategy. I should mention that in the transfer learning literature, there are actually different ways to go about updating this network. There's pretty interesting ideas behind this. One of them basically says that instead of just take the entire network structure and then the initial parameter values like we do and then update them based on new data, you actually try to replace part of the network. Imagine that you have, let's say, 10 layers in the network. You wipe out the top 3 layers. For what reason? Don't really know, but people have argued that that might be a way to essentially more actively bring in new information. Another literature will basically freeze part of the network, not letting it move at all. Like the bottom layer is not giving any opportunity to update, and that's another extreme way to basically preserve the information or knowledge you learned from the simulated data. Yes, Chen?
So one question is, so what's a sample size for these 2 steps?
Absolutely. So I'll give you a more specific analysis about this, but roughly speaking, right, in the second step, we just have all the data, empirical data we have. So that's deciding the size of the sample there. In the first stage, you have the luxury of generating data you want. So in one line of thinking is basically, let's just generate as much data as we can, right? That's kind of what's fits into our budget constraint, basically, right? Alternatively, you might be worried. Actually, this is a point I don't want to explore, so maybe I'll hold on to that. There's another thinking, which is that maybe bringing too much similar data is not good. In fact, if you understand the literature or the idea behind this kind of Bayesian VAR using prior, they actually have a very nice result showing that the performance improvement is in a kind of U-shaped pattern in relation to the sample size is similar. And there's a reason behind it, we'll explain in a second.
I have another question.
Yes.
So here, because you are using some supervised learning framework, but when we have see the data, we don't know which one to label, which one to input. So how do we choose the label and other things as input?
That's an interesting question. So in our setting, I would argue that our distinction is pretty clear. Right? So we're basically trying to predict some equilibrium quantities such as option prices, and we're using all the inputs we can possibly imagine to predict that. And when you commit yourself to a particular structural model, then that model will have a very clear list of relevant inputs as well. But you're right that in more general settings, it could be that you are trying to understand the relation among multiple endogenous variables. It's related to with this question earlier as well. So I can't say I've completely worked out that setting. I think there is still a way to basically do, say, multi-target predictions that could actually allow you to address the joint kind of restriction among multiple variables. But I shouldn't speculate too much because it's outside the scope of current.
So thanks. I think this is really cool, but I'm trying to understand the state from an optimization point perspective. So to me, it looks like, okay, you use the theory to get your starting values.
Correct.
If you want to call it that, to go to the data.
Yeah.
Now, if you're not Bayesian,
we're not Bayesian here either.
no, I know, but like, what it's a very, very noisy, very difficult optimization problem with a lot of values and a lot of things. So, what if you're in the wrong value with your initialization, right? Then, in a sense, do you have any diagnostics or any suggestions of any sanity checks? Because the way you do it is you're putting a lot of weight on the theory, and I'm a macroeconomist. Everything I do, I know it's horribly misspecified, right?
Well, I'm trying to give you more hope, by the way. And hopefully, by the end of this talk, you have actually more pleasant feelings towards those models. But anyway, I get the point. This issue about we're actually not being able to fully solve this optimization problem over here, either in the source domain or in the target domain, is pretty well known, right? So this is the kind of optimization error we have to live with. In the source domain, it's relatively easy to check how close you are in terms of matching those actual quantities the model can predict, because we are playing God over there, right? We know what the true data generating process is. In the target domain, it is admittedly much harder. Usually what people do is they observe the how the empirical losses behave as the number of epochs increase, and see if you are in some kind of valley, and wave your hands and say it's good enough, and then you don't.
But you have like Monte Carlos, where you say you start with some parameter settings, and then how much do you have to change the model for it to not be able to move to that new set of parameters, right? So something like that could be.
Let me think more about that. That is interesting stuff.
Yes. You
Yes,
can create a data set from a known model, right?
Correct.
And then you could pick some other model that's incorrect and use that as pre-training. And then see how it works. And then
Beautiful, yes.
Exactly.
That was exactly on our to-do list in terms of trying to. So the idea, basically, the discussion is basically about, like, intuitively you would like to think that if the model restrictions are valid, you should learn more from it. But if they are horribly specified, maybe they actually hurt rather than help. Although that's debatable to the extent that if you believe this kind of philosophy of kind of bias variance trade-off, right? It could be basically imposing some really random restrictions, but it still helps you more in terms of reducing variance. And even though it hurts you in terms of bias, so be it. So it could potentially still be helpful. But I think this kind of controlled experiment could be very well worth doing that. It's exactly on the list. Very good, thank you. So I should keep going. I do want to show you in the last part of the talk here a finance-oriented exercise. So please don't turn away. At least there's something potentially interesting going on over here. Okay, so the exercise we're going to do is basically try to predict option prices. Right? We're going to use a few alternative approaches to do this to run a horse race. One of them, obviously, is going to be our kind of transfer learning approach. Right? So combine a structural model with data. The other approach will be a standard, off-the-shelf deep learning, deep neural network. We call it DNN. Right? And by the way, we're going to choose a massively misspecified model that everybody knows about, which is the Black-Scholes model. We know that it's a very simple model. It has it was beautiful in the sense that there's no need to specify prior on the parameters. There's no parameters that are actually not directly observable. It's going to be directly feed into the data, into the model. But you know that it doesn't fit the data well at all. It can be easily rejected. Okay. All right. Now we're going to augment. So this is the second part here. We are interested in seeing that can we kind of potentially pick up things that are outside of the model as well. Right. So we're going to pick some other features such as pass returns, beta spreads, and group ratios. All of these are completely outside the realm of this structural model we're working with. Right? We know that they're irrelevant according to the structural model. So how would you generate this kind of data from the joint distribution according to the theoretical model? Well, we're going to just randomly populate these entries over there. Right? As we pull out the data from the structural model, like the stock price, strike price, and so on and so forth, we're going to randomly fit in these models so that again, the structural model thinks that those are irrelevant features. Okay. All right, so altogether, we're going to have 16 inputs, including the structural Black-Scholes inputs as well as the other inputs we put in there. The architecture is a pretty deep ResNet, so we're using this residual network because the layer is number of layers is pretty high. There is 22 neurons in each hidden layer, and then we're using this leaky rate activation. If you're interested in the architecture, I'll be happy to talk more afterwards. At the end of each quarter, so we're going to try to kind of do this in a rolling approach, right? We want to do out of sample prediction. So at the end of every quarter, we're going to look back for 3 quarters. That's a total of 9 months of data. We'll use this data to form a training data set for the target domain. Right? With the source domain, you don't have to update, right? You just do that once. You do that once and do it well, and then you'll be done. But in the target domain, every time will give us a new branch, a batch of 9 months of real data. Okay. Now you might be wondering, okay, we actually potentially have more data. As you move forward in time, you're going to have bigger and bigger data sets. That is true. We do this for 2 purposes. One, we want to mimic this environment where we have limited data, right? Which is ultimately why we are interested in working on this in the first place. Hopefully, these theoretically guided kind of starting points can actually save us in the demand for data. Secondly, in the financial data settings, at least, you often run into this kind of a non-stationary, right? Things could actually change. What you learned from the past may no longer be valid. So it's actually routine for people to do this kind of moving window approach. That's exactly what we do over here. All right. So, and then we once you train your model in the target domain, now you're ready to do forecasts. So you can now make forecasts for option prices in the next 3 months, right? These are quote unquote out of sample exercise. You can compare the pricing errors for these different approaches you can throw at the problem. We'll also throw in a Hessel model, which is a completely structural model, and then also a multi-target DN model, which we'll explain in a second. All right, so I'm going to show you the results. This is the baseline result over here. You'll see that what we're plotting is the out of sample mean absolute errors, pricing errors over here. The solid line, red line over here, is the result from our transfer learning exercise. In case you're wondering, the black dotted line is the off-the-shelf deep neural network. You can see that the out-of-sample pricing error is quite a bit higher, but in some episodes, such as the financial crisis, and more recently during the COVID pandemic onset, it actually was substantially higher. Another line on this picture is the Hessel model. So this is using just the structural model itself. You basically refeed the structural model parameters using that 9 months of data as your training window, and then you make forecasts just like we do in this model here. And then you can see that the performance was actually pretty bad, and in later periods in particular, it was actually substantially underperforming even the deep neural network. All right. All right, so it will be interesting to try to understand what's driving the performance difference, right? In particular between the red line over here and the black dotted line. So we do some kind of a performance attribution over here, which is pretty simple using regression analysis. You find that the transfer learning model actually has a bigger advantage over the deep learning model under the following scenarios. One, when the market volatility is high, as measured by the implied volatility IV index over here, you find a bigger gap between, which is kind of intuitive in the sense that when market is volatile, perhaps the structural model is, this kind of a completely data-driven approach, right? Using the empirical relationship we learned from the last 9 months, will have a harder time to extrapolate into the next 3 months, which is perhaps why they underperformed. Another hopefully intuitive result is that when inputs are appearing unusual compared to the 9-month data you have in the past, which by the way we measure using the Mahalanobis distance, again you find that the performance lags, right? So this same intuition, right? What you're trying to predict in the future looks more different from what you have in the past. So extrapolation just doesn't work so well. Whereas perhaps this kind of structural model guided prediction is more stable. Also for options with lower beta spreads, it seems that they perform better. So that's basically saying that the structural model perhaps in a way is kind of binding your hands a little bit when the actual data behave more differently, right? When the options are illiquid, these kind of a structural model that ignores the liquidity in the options market actually having a harder time. So this goes back to this perhaps more specified model may at some point may actually hurt you instead of helping. And then options with the shorter and longer maturities tend to do better. That's because that's where the sample size is more limited. We have most of our options are actually kind of between 1 week and 1 month. And when you go too far down either side of this maturity spectrum, that's where you have a more severe lack of data from. And that's why the deep neural network actually struggles more. Okay. All right, so this, by the way, is basically checking what if you relax the assumption that, or a restriction that we can only learn the deep neural network using past 9 months. That's actually using expanding window rather than moving window, right? To use all the possibilities in past. And you see that actually does help, right? So you get to move from this black dotted line, which you saw from the previous slide, to this blue dotted line over here. So you can see that as the sample size grows, the trend is that it is actually performing better and better compared to the black dotted line. It doesn't fully cover what the transfer learning does. And in some episodes, such as the crisis, financial crisis and the pandemic, it does diverge pretty substantially. So the same caveat still applies there. But it's no denying that more data it will benefit these kind of parameter heavy models, which is not surprising. Okay, so next we want to try to do some empirical analysis to get a better understanding of what is the source of better performance. So for example, is it because that the theory is simply just helping us identify the relevant features, right? The structural models tell us what are the relevant state variables you put on the right-hand side and nothing else. Maybe that is where we learn things. Is that what's going on? We can actually compare. So we would actually deliberately do a side-by-side comparison. This is basically transfer learning with a full set of 16 features versus transfer learning with only the Black-Scholes features. You can see that if anything that deteriorates the performance because there is, after all, more things you can learn beyond what the structural model does. And very interestingly, things reverse itself when you do the same exercise for the deep neural network. If you do the deep neural with a full set of 16 features, you actually run into more overfitting problem, seems like in our experiment. Whereas if you regulate it by using only the Black-Scholes inputs, most of the time actually do a little bit better. The performance is not that substantial per se, but it's actually tend to be better performance rather than worse. Exactly reverse basically in the transfer learning exercise. All right. Really kind of short on time, so I'll be a little bit quick over here. The second thing has to do with whether it's simply about having more data, right? This is basically the intuition of the Bayesian interpretation. In the Bayesian approach, effectively, you are basically averaging over what you can learn from the simulated data and the actual data. And in particular, this is a nice way to understand the relative sample size question. So if you have a lot of simulated data from the structural model, the actual final result will be more heavily influenced by the structural model and vice versa. That's why you get this U-shaped pattern, right? You don't want to not having a structural model at all, but you don't want to have too much structural model influence either. Actually, sweet spot somewhere in the middle. In our case over here, you can see that we can actually easily check, right? We can just simply pull the real data with the simulated data together and let the deep neural network learn and see if the performance can actually match what the transfer learning does. And the answer is clearly no. Right? It actually doesn't move the needle much at all. Next, we can actually regularize the deep learning problem in a slightly different way. We can actually try to set a target such that not only you want to match the actual data, but perhaps you also want to match the model prediction as well. This is another way to do regularization, but we don't really have a clear indication whether this is better or worse. So we check on that, and we find that the answer is no. Right? So it's really something different. One very quick thing on this is that, in fact, we can impose very weak restrictions as well, such as a model-free, no arbitrary restriction. In that case, you find that the result doesn't really improve that much. So perhaps that says that even though you can impose these restrictions, and there's nothing wrong with it, but if these restrictions are too weak, right, you can already learn from the data directly anyway, then it doesn't help you in this translearning framework. So I should really just wrap up. In conclusion, I hope you can see that we are basically trying to do a hybrid approach, right? Take the model we hold dear to ourselves and assimilate data from that to help guide our learning from the actual data. And I will part the lecture with this talk with this sentence here. Instead of thinking the theories are dead, I think it's a good kind of a message for the people, particularly this audience, that we can potentially benefit a lot from having kind of a hybrid approach of structural modeling and empirical data learning. Thank you very much.
Well, thank you.